Thank you very much. First I would like to thank you, my committee, Dr. Ashton, for inviting me to this talk. I'm so delighted to come back after graduation last year. Okay, so this is the topic today is called Selective Linearization Algorithm for Solving Multi-Block Statistical Learning Problem. And this is joint work with my advisor, Andrei Ruskinsky. The methods is designed to solving multi-block convex non-smooth optimization. I will give some examples and problem formulation. The method is derived from the ideas of proximal point, operator splitting method, bundle methods, and the proximal decomposition via alternating linearization method. So I will have a review of that method and then formally introduce our method, and then we have also derived the good convergence result that we proved global convergence and convergence rate. As we derive these convergence rates of slim methods, we happen to solve the open problem for convergence rate of classical bundle method. At that time, when we submit paper, there's no convergence rate result, so we happen to solve this problem. And then later on, I will demonstrate the methods using some multi-block statistical learning problems, such as fused lasso, overlapping group lasso, and regularized support vector machine problem. And in the end, I will conclude my talk and describe some of my ongoing research work. So in the area of machine learning data mining, we know that we always encounter the big data challenge. Either the data is in large size or in streaming data, or the data is in high dimension. Especially, for example, in computer sensing or bioinformatics, the data size is quite smaller than the feature size. So by traditional regression classification model, it's hard to estimate those number of features with limited number of sample size. A lot of application can cast into these frameworks with loss function and a summation of structured penalties. So for example, this Netflix rating problems, people try to submit rating to the Netflix movies, and then the resulting problems try to reconstruct this matrix so that we can give recommendation on to what to watch next. And the resulting model is just 3-block structured regularization problems with L1 penalty that group people with a similar preference, and also the matrix has to be low rank properties. And the other example is like overlapping group lasso in dictionary learning, where we have a loss of function and then summation of overlapping group features. So it's applied in this dictionary learning. For example, we have backed words, and then we can, based on the syntax structure of the sentence, we can build up a tree structure feature. So for example, the hit is one subset of verb and another subset of verb phrases. So based on this structure, we can find a hidden topic from the backed words using this overlapping group lasso base, and the features can overlap. So this is non-separable multi-block problem, okay? And it's non-smooth. So the problem formulation is this summation of multi-block non-smooth function. And we designed the algorithm to can solve this problem. And we have proved the goal loop convergence and convergence rate of 1/k with 1 out of n function being strongly convex. And this result is published last year. Okay? So the selective linearization comes from the ideas of proximal point, operator splitting methods, bundle method, and the alternating linearization method in 1999. And we know that proximal point method, instead of solving a convex function, we are solving a proximal steps of the convex function by adding up approximate terms by making this problem strongly convex. And then by Rockefeller, we know that the proximal center will converge to the minimum point. And different from proximal point, bundle methods replace the fx by a piecewise linear lower approximation of the function by a cut plane bundle of it, which is defined as this. And then after solving this each proximal steps, the solution of these proximal steps will subject to a sufficient improved test to decide if the solution makes the function value has significant decrease. If it's a significant decrease, then the proximal center will change. Otherwise, it will not change. Okay, so there is a picture demonstration on coupling methods of this coupling approximation. So at each iteration, this coupling approximation will get closer to the original function value. Okay, and there are many versions of classical bundle method with card aggregation and multiple cards. So we know that at each iteration, we will solve proximal steps. And then after this proximal step, the function, this solution will check if the solution is making this gap as closer as possible to the original value. And then we're going to do this update test that if the current solution makes the function value has significant improvement, we call it update test with parameter beta. If we make this proximal center change, we will call it descent step. Otherwise, we will call it null steps. So this bundle method will consist of many null steps, and then a descent step, and then many null steps, and one descent step. Okay? And then we will update the multiple cut by the newest cut. And we can also do the bundle method with cut aggregation by instead of all the cuts adding up together, we will consider the recent cut and the convex combination of the previous cuts. Okay. Right. So in the paper of Kiwi Ruskinsky in 1980s and 1970s, it proved the convergence of bundle methods that the solution of each subproblem will converge to the proximal center. It will converge to a minimum point. And because the difficulty to analyze this update test of this descent step, and then the convergence rate is an open question. And then in last year, we managed to prove bundle methods which will have the convergence rate of O of log I1 of epsilon over epsilon with the strongly convex condition, which is strong, but is one way of prove it. Okay. So selective linearization algorithm also coming from the ideas of operator splitting methods, where we try to so operator splitting methods for solving two-block convex function is we try to minimize this two-block function, and then we process two maximum monotone operator together. Okay, because to process two monotone operator is hard, then we kind of fix one operator and then process one, and fix another operator and process the other one. And there are many types of monotone operators, and I guess all the audience are very expertise on that. And then there are dual version of operator splitting methods, which is called standard ADMMM, which is kind of fix one, for example, y variable, and then solve the minimization with respect to x, and fix x variable and with doing the minimization over y, and update the Lagrangian multipliers. So different from ADMM methods, the alternating linearization method in 1999, they use the idea of operator splitting method and the bundle method combined together, okay, and then they prove the global convergence and utilized into some statistical learning problem, and it shows very good, like fast performance. And the idea of alternating linearization method is trying to minimize also two-block function, non-smooth, and at each iteration, we're going to linearize one function and keep one function and add a proximal center term. The way to linearize is with use the subgradient information. Okay, at the first iteration, we will do the explicit calculation of subgradient. Later iteration, we only get the subgradient information of h by the KKT condition of these proximal steps. Okay, and this is a good way to get the newest subgradient, and also we also save storage of the subgradient, because update of subgradient is very limited. We only need to store the latest iteration of subgradient. Okay, similar to bundle method, at each step we will evaluate if the current solution make the function has significant decrease, then we will update the proximal center. Okay, otherwise we don't. And then use the idea of operator splitting method. This time we will keep f function and then linearize h function plus approximate centered. Until end, we stop the algorithm. Okay, so slightly different from the previous proximal point methods. We are using a diagonal matrix D as a proximal parameter for simplicity of computation. Yeah, so there are many applications. We can select different D based on, for example, the form of loss functions for simplicity of computation. Okay, so selective linearization is a multi-block extension of alternating linearization methods for solving multiple monotone operator problems. Okay, so we are minimize a convex non-smooth function, summation of it, and then at each step, we are solving proximal steps, which we fix one function, keep as same, and linearize all the rest, and plus a proximal center term. And because at each iteration, we will treat one function exactly, and then linearize the rest. So we have a selection rule that will select one that has the largest gap between its function value and its linear approximation, because that will make this gap, to make the improvement first. And it's the easiest way to prove convergence and convergence rate. And we know this is fourth order linearization of fx, and proximal center will change based on the update test. And also, this f function will be linearized using subgradient prepared for the next iteration. Okay. So at the end of iteration, we're going to evaluate the stopping test if this gap get very closer, like the function value and its linear approximation gap. Okay. And also the update rule check if the current solution makes the function value has significant improvement. Okay, that makes our algorithm will have monotonic decreasing procedure. Okay, and it's converge very fast. And then we will derive the gradient from the KKT condition. Okay, and then we have to select the next function to treat exactly, and using this selection rule that calculates the difference between the function value and the linear approximation. So the convergence analysis of this Selective method is very similar to the bundle method and alternating linearization method. And we rely on the assumption as the subgradient of a convex function is locally bounded. Okay? And we have proved that the solution of the subproblem is converged to the proximal center, and it converged to the minimum point value. And we also prove that the optimal objective function value will converge to the function value evaluated at proximal center, and it will converge to the minimum fx star. Okay. Right. So how do we prove the convergence? First, we prove that the optimal objective function values of each subproblem is increasing because its lower bound is getting closer to the origin function. And then it's increasing, but the gap is bounded by a quantity is this one. So it's increasing and it's bounded by this value. So this is lemma that shows at each step the subproblem is increasing and is bounded by a quantity. And this is based on the assumption that the subgradient has to be bounded by a parameter m. Okay. And we have shown that it is increasing and it is bounded, and there is we have to estimate the step size of each increasing, which is this lemma. Okay. And based on the previous analysis, we can prove that the convergence in the case of finite many of descent steps and infinite many of descent steps. If we have many, if we have finite number of proximal center, or we have finite number of descent steps, then the last proximal center will be the minimum value. Okay. If we have infinite number of proximal steps, we will see that proximal center will converge to the minimum value x star. All right. So next step, how do we prove the convergence rate? So to prove the convergence rate, we need an assumption that capital Fx, summation of a lot of non-smooth functions, has to be strongly convex with parameter alpha. Sufficient conditions, 1 out of n function is strongly convex. So to calculate how many number of iterations we need to bound two issues. First, how many number of proximal center will be generated, and then how many number of null step in between two consecutive proximal centers. Okay, so the one assumption we need is this capital F is strongly convex and unique minimum exists. Okay. So first, we have shown that at every iteration k, we have these inequalities. Based on this lemma and strongly convex assumption and the updated test, we have proved there is a linear rate of improvement between consecutive descent step. So there's linear rate improve between the proximal centers change. Okay, and then based on this update rule and the stopping rule, the proximal center will be updated only if this inequality is satisfied. Then we can get the upper bound for total number of proximal center generated. Okay. So this is demonstration there is a linear rate of improvement between descent steps. Okay. But there are many null steps in between. How do we estimate the number of null steps is small? Okay. So the next step is to try to estimate the number of null steps between two consecutive descent steps. So we do the analysis based on the gap of the function value minus the optimal subproblem of function value. Okay, and then we have shown that there is a sublinear rate of improvement between two consecutive small null steps. Why sublinear rate? Because there is epsilon still inside of this, which can be improved because in real application when we do the test. Is way much better than this, so it's possible to improve these results. So how do we calculate how many steps in between two consecutive proximal centers? So we take a look at 3 consecutive proximal centers, and we try to estimate how many number of null steps in between one proximal center XL. Okay, so we need to bound the gap for the first step of inside of this proximal center, and the bound for the last step of this proximal center. Okay, we need to bound these two gap. So we have shown this. The first step of the gap is bounded by the difference that has information of the previous proximal center, and also by the previous lemma, we have then shown that the last step gap is bounded by the information for the future proximal center. Okay, and because they are sublinear rate increase, and it is bounded by below and above, so we can calculate total number of null step inside of each proximal center. And by this excellent constellation rule, we can estimate the total number of null steps when we add up together. And then we do a special treatment for the first null steps, first proximal center null step and last proximal center null steps, and adding up all the null steps. Because of the good constellation rule, we can get these results. And we know this is the previous proximal centers, right? And then we add up all these together, we get the upper bound for total number of descent step and total number of null step, which is log 1 over epsilon. So this information this bound has information of the beta and the subgradient bound, the number of blocks, and also the strongly convex condition. And we try to minimize this total number of steps with respect to beta to get a theoretical suggestion for this beta, which is exponential to the very long formula. Okay? But we also do some experimental tests says beta is better to choose, for example, 1 over 2 as a good choice. And then so this is our convergence rate result. We have to achieve precision level epsilon. The total number of steps we need is 1 over epsilon, O of log 1 over epsilon over epsilon. which is equivalent almost 1 over k of convergence rate. Okay. So next step, I'm going to discuss how do we utilize the methods into some multi-block statistical learning problem. For example, this is a very easy, example, like the 3-block fused lasso problem. Okay, and then to solve this, we just need to every step we need to fix one and linearize all the rest. Okay, and here we use D. Remember we talked about D in the proximal center parameters. We use diagonal A transpose A because the loss function is this form for simplicity treatment. And then we to solve this problem, we treat F1, and then linearize all the rest. This can be solved by precondition conjugate gradient method. F2 is a closed form solution. Okay. F3 is we treat this one exactly and linearize all the others, use subgradient. And then this can be solved by a box constraint conjugate gradient method or block coordinate descent methods efficiently. Okay. And then I did the comparison with alternative linearization methods and the Douglas-Rashford methods with over relaxation, under relaxation, and choose different proximal parameters. And it shows that slim methods always get the smallest iterations with different size of problem and with different dimension of problem. And also the time comparison as well, we have the lowest computational time. Okay. And the next example we do is this overlapping group lasso we discussed before, which is a loss function plus a summation of overlapping group features. And for example, we can have many k groups, and some features can overlap. So it's a non-separable problem. And here D, we choose 1 over k lambda diagonal A transpose A. So to solve each subproblem, it's very similar. We have to treat this loss function. And it's kind of solving a linear system equation can be solved by precondition conjugate gradient method. And the Fj subproblem is treat one function of this group and then linearize all the loss function and all the rest overlapping features. Okay. To solve this problem, we treat the decision variable that outside of current group is a closed form solution. Inside of this group, we solve it by first order conditions of this subproblem, and then we solve it by bisection method for this. And then we first did a very simple example on the tree structure overlapping lasso with Vista, and it shows we are better in terms of time, but it's very small example. And later on, we try on the fixed order overlapping group lasso with 100 groups that has overlap of 10 variables in between two group of features. So it shows that, and we compare with PDMM, ADMM, PAAPG, SAPG, that we have comparable results with PDMM, which is very special, is a code for parallel ADMM methods for solving this problem. Okay? And we also do a time comparison. Yeah, but this one we are kind of slower than the PDMM method. But later on, we try on the random generated overlapping group lasso. In some gene problem on topology, some of the feature overlap that can be random assigned. Okay, then we do this test and compare with PDM methods, and in most cases we are better than these methods. Okay, later on we try the examples on regularized support vector machine problem because we assume any function can be non-smooth. So we look at these non-smooth loss functions, which is like a less than net SVM problem. And this solution should have both sparse and grouping effect. So the difficulty is try to solve this each Fj subproblem. Okay, so we can treat the whole summation of this loss function as one group, but it still can be solved by active set problem, but still is a little bit too much work. So we treat, instead we treat one of of these fg functions exactly, and linearize all the rest of the fg function and all the subgradient of the other regularization, okay? And then we can solve it very quick, like closed form. So it's like we treat this problem as a constraint and look at each the constraint is active or not. For example, this at first case, this is active. Second case, this is active, or the both case is active. Okay, and then we solve it during these three cases, and they all like linear equation to solve it. And then we compare with these methods with a paper in SNet ADM method, and then it shows that we are better in terms of computational time. Okay, so yeah, this is end of my talk. We introduced this selective linearization algorithm for solving multi-block non-smooth convex optimization, and it proposed one operator splitting methods that can guarantee global convergence, and for any arbitrary number of operator results, duplication of variables. And we are solving the primal problem directly. Under the strongly convex condition, it proved convergence as O of 1 over K convergence rate. It's also a major contribution. When we solve the problem, we go back and prove the convergence rate for bundle method, classical, and publish another paper. And at that time, there was no convergence rate result. And we also did some comparison to demonstrate how do we use this method, and it shows the efficacy and the efficiency of our method. Okay, and right now we are trying to extend the work to solve some prove the convergence without this strongly convex condition. And this is a still ongoing process, and then we try to extend to solve a non-convex problem. That's also our purpose here. And also, we try to estimate this minimization problem with respect to a linear operators inside of this convex function, and then try to design the stochastic version of these slim methods to solve some large scale problem. Okay. And this is the related paper regarding to this talk. Okay. And thank you very much.